Good afternoon. Welcome back to ECE 207. We've had our commercial period. Now we have the uninterrupted scheduled event, which is the class, ECE 207. For those not behind a computer, you can actually see the other screen, which is actually a commercial, but if you are interested, I am going to have a sign-up sheet at the table outside of the South Ballroom in the Student Union tomorrow afternoon. There is a special, ECE is celebrating their 100th year of being in existence. I know I graduated from the program back then. No, not quite. I'm not quite that old. But if you are interested, this is a speaker from Cirque du Soleil, and he's the head of automation for O. Some students, I guess, have already seen that or know a little bit more about that. He may show some videos about that, and maybe you'll see some of this material put into use that we're learning in 207. That would be nice. Maybe I'll suggest that over lunch. How's that to him? Today what I want to talk, and homework number 5 has actually been delayed a week in terms of when it's due. If you have it finished, that's fine. You hopefully just hold on to it. We will have a class participation problem halfway through today's lecture. If we could pass those to the appropriate sides of the classroom and then pass them forward, and then I only have 3 piles to collect at the end of the class is the idea. For today's material, here's our laundry list that we want to cover, or our shopping list, whatever you, maybe you prefer to shop than you do laundry. I don't know, I seem like I'm doing both of those all the time, so it really doesn't matter. We're going to define complex power. Does anybody do complex laundry? I don't know where that came from, but if you have clothes that are in the imaginary axis, come see me and maybe I can tie those into the lecture. But most of our laundry is probably on the real axis. You want most of your power to be on the real axis also, but we will learn on down how to maybe bring most of our power along the real axis if some of it is in a different direction. Either positive, which is a lagging, or an inductive power. We'll maybe try to bring that down so that it gets more at a 0-degree angle for our complex power. And we'll do that by introducing a capacitive load and introduce some leading phase for our power angle correction, or what may be called power factor correction. We'll try to get through that, but I keep showing my arm mainly because I need to get some exercise. I don't seem to be getting any. No, but it's the power triangle. Maybe we need to get up here and lay in triangles or something. But we're going to have a real part, an imaginary part, and hopefully that won't be as long as the real part, and their combination gives us complex power. And you need to start thinking or visualizing that when you start seeing these complex power problems. If you have multiple loads, each of those loads in general can have a real part and an imaginary part, and you simply have to add up vectorially those real parts and the imaginary parts to get your total complex power. Let's now work with what we, I think, have already defined. Which is this complex power expression. And we're going to use phasors. That's what the bars are for. And our complex power associated with a load, associated with loads, associated with a source, will be the voltage phasor times the complex conjugate of the current phasor associated with that load or source. That's what the asterisk or the star in the superscript means above the I, which if we look at that in phasor form, or more explicitly, we have this VRMS, which is a number at some angle, theta sub v. We have our current magnitude written or determined to be in RMS units, meaning if it's a maximum current, you simply divide by the square root of 2 to obtain the RMS value. We're going to be dealing with sinusoidal voltages and currents, and that's why this square root of 2 factor occurs. You can go through the algebra and figure out that if you find the RMS of a sinusoid, it's going to be maximum value over square root of 2. That's where this square root of 2 comes from. Then if the current has an angle of theta sub I in this complex power expression, we now need to negate that angle to obtain minus theta sub I. Or this now simply becomes the product of our two magnitudes, voltage and current, and the angle or the phase of that complex power is really the difference between the voltage phasor and the current phasor. If we go a little bit beyond this phasor notation and invoke Euler, that angle symbol actually expands into an e to the j at that angle. That's really the shorthand notation that we've indicated right there. If you write that in terms of using the Euler relationship for e to the jx, where in this case x is theta sub v minus theta sub I, we can now expand that angle term into a real part, which the real component is just the cosine of that angle, plus j times the sine of that angle, where that angle is the difference between our voltage phasor and our current phasor. And we might simply write that. We may say, you know what, let's just call that difference a theta. Instead of theta v minus theta sub I, sometimes we might just say, all right, we have VRMS, IRMS, cosine of theta, plus j VRMS, IRMS, sine of theta. Where this piece is the real part of our complex power, and that is what we pay for in a residential sense. That's watts. That's our P average. And this other piece is our VARs, which is combined in a complex form. We have P plus JQ, and the units on these are watts, VARs. You'll enjoy saying that when you're doing your homework. Oh, I have some VARs. And you have some volt amperes, some VAs. Meaning if I say, oh, your load is 16 kVA, then I'm really telling you the particular piece of that power formula that I'm giving you. I'm giving you the complex power. Maybe I'm just telling you the magnitude of that. And that's the apparent power. Let's make some observations relative to this red and blue expression for complex power. So this is what we call our complex power. It has a real part and an imaginary part. And let's now make these observations. And it's really just algebra with the complex numbers. The magnitude of S bar has two parts to it, or it has a real part and an imaginary part. If we want just the hypotenuse, or the magnitude of that, we could find V RMS, I RMS, e to the j, theta v minus theta I. That's one way of viewing that. This is just another way of writing at an angle of theta and trying to convince you that that angle piece does not contribute at all to the magnitude, where the magnitude of e to the jx is, well, if you can't see it, but that's this rotating phasor. E to the jx by Euler is cosine x plus j sine x. If I say, what's the magnitude of that complex number? You have cosine x for the real part. Let's square that. Then you have sine x for the imaginary part. Square that. You now have cosine squared and sine squared. And everyone's seen the t-shirt, correct? That you might wear it, maybe it's not a t-shirt, but did you hear the joke about the young man at MIT, and he said, he goes up to a lady and he goes, "You must be sine squared." And she goes, "What?" He goes, "You must be sine squared because I'm cosine squared. Together we're one." Sorry. So cosine squared plus sine squared is 1. E to the j theta, what was I doing? I'm trying to tell you that that has a magnitude of 1, which means we can now forget that piece. And we now simply have the magnitude of v times I, but the magnitude of a product is the product of magnitudes.
I'm still not sure why the magnitude of e to the j theta is 1.
You didn't like my joke? Or maybe you got too sidetracked by the joke. Let me say this is what we call the apparent power, and then I'll go back and try to answer the question of why is the magnitude equal to 1? Is that your question? Where x in our case is this theta sub v minus theta sub I. I'm thinking that you all are okay with writing this cosine x plus j sine x. That's Euler. Now you should feel comfortable with the magnitude of a complex number being the real part squared plus the imaginary part squared square rooted. Meaning we take the real part and that gives us cosine squared. That's the boy in my joke. Then you take the imaginary part. Maybe that's the joke. The girl was imaginary. It was at MIT. Sorry. I just thought of that. Sorry. We're trying to improve that ratio. Okay? And it's better here at the U of A, maybe. Maybe, I don't know. But now, does that make it, do you believe me now? Okay. All right, cosine squared plus sine squared is 1. E to the jx is cosine x plus j sine x, and now I hope that I've convinced you that that has a magnitude of 1. Meaning, if we want the magnitude of our complex power, that's the magnitude of this number, S, or vector S, and that's just the apparent power. We'll call that the apparent power. We also have average power. And that's the real part of this complex power. Meaning we take the magnitude of the voltage, magnitude of the current, and scale that by cosine of theta sub v minus theta sub I. That has units of watts. And we may call that the average power or the real power. And you could think of that as the real part of that complex power S bar. Again, we're just making observations with respect to this complex number, S, which you can find by finding the voltage phasor and the current phasor of whatever it is that you're trying to find the complex power of. If it's a load or supply, you just take V times I star and you'll get a complex number. The real part of that will be your average power. The imaginary part will be your VARs. That's what Q is. Oh boy, I'm sorry. I've had maybe too much to drink before class. I was going to say we're watching our P's and Q's in this lecture. So we have our P's, average power, and our Q's, VARs. So here is VI sine of theta V minus theta sub I. That's the imaginary part of the complex number. Too much to drink, meaning too much caffeine. That's why I'm pacing. VAR, volt amperes reactive. We call that our reactive power. Or that's the imaginary part of S bar. One more, excuse me, one more observation. Our power factor. We can think of that in several different ways. That's what the apparent power is reduced by to get us our real power. Or you could say, well, that's the ratio of our real power or average power over the apparent power. The apparent power is just the magnitude of S. But what's P average? P average is the magnitude of S times cosine of theta. We take the ratio of that, and that's now just the cosine of theta sub V minus theta sub I. That is our power factor. And typically, we may need to be told more than just the power factor. The cosine of x and cosine of minus x, what do those look like? They're the same thing, aren't they? It's an even function, cosine of x. Meaning, we may have to be told, is this power factor a lagging power factor or a leading power factor? You may be told more information. If it's lagging, then your load or whatever this is expressing looks more inductive. If it's leading, it looks more capacitive. And Eli and ICE will help you maybe remember that information. Eli, where's the voltage? It's in front of, so your current lags. And this is inductive load versus ICE. And now your current comes in front of the voltage in this expression, or we'll say that the current leads. And that's a capacitive load. Those are our observations relative to complex power. We have a real part, average power, an imaginary part, VARs, an apparent power, which is really the length of our hypotenuse, or the length or the magnitude of our complex power, and we have the angle. And one way that we can keep track of all of that is simply to draw this triangle, and that triangle is called the power triangle. where it's defined by S bar, and we can write that many different ways. There I'm meaning the angle of S bar is just the angle of that complex number, whatever that complex number is going to be, or that's the magnitude of VRMS IRMS times the angle, which is the difference between our voltage angle and our current angle, and sometimes we just abbreviate that to an angle theta. That expression can give rise to the following plot. We now have the real part, which is P average. We have an imaginary part, which is Q. There are P and Q. And then we have, whoops, that's supposed to go to the tip of that Q. This is now of length S and angle theta. If I just gave you S bar, that would be that vector that's at a length or has a length of the hypotenuse of that right triangle formed by the real power and the reactive power and that angle theta. Question?
On the S bar, should that sit next to S, the phasor theta?
I'm sorry?
Should the phasor be theta or should it be S bar?
So the question is, should the phasor be theta or S?
You see the phase angle, that's a phase angle?
So this angle is theta.
Right, but you wrote it as S bar.
Oh, I'm meaning S bar is this length.
Right, as the magnitude, and in the phase angle you also wrote it as right above.
Right here or right here? What I'm meaning here is that's the angle of S bar. So so that's notation. This means if I had S bar of 5 at an angle of 30 degrees, then if I say the angle of S bar, I'm saying that that's this angle 30 degrees. Does that make sense? I'm just using sort of a shorthand notation. I'm just saying the angle associated with that complex number S bar. So if you know what S bar is, all that means is, oh, take the angle of that. Does that answer your question? I'm sorry, I didn't understand the question, obviously. So I'm going to erase that. Oh, I should know better. That's our power triangle, where our P average is hopefully from that picture. If you forget what all of these are, just draw that sketch. Then you have P is the magnitude of your complex power. That's your apparent power times the cosine of theta. If you want your Q, that's just the opposite side of that right triangle, which is the magnitude of your complex power or the apparent power times sine of theta. You may be given P and theta. You may be given P and a power factor. You may be given S. You may be given the magnitude of S and an angle. There's a lot of ways that I can give you this information, and you should be able to then sketch or draw the triangle to tell you what you have for average power, what you have for reactive power, and what you have for complex power, apparent power, etc.
Where does the power factor come in on this chart?
So where does the power factor come in on this triangle? It's now the cosine of theta, meaning the power factor is defined to be the cosine of theta, which means that that's this piece right there, meaning it scales the apparent power in a way to give you your real power. It's not explicitly in that diagram, it's implicitly shown or indicated by theta, where the power factor is the cosine of theta. The only thing that you have to keep track of, or another thing that you need to keep track of, I've sketched that picture for a positive theta. Theta will be positive. Remember, theta is theta sub v minus theta sub I. That means your voltage angle is bigger than your current angle, or the current lags voltage. And in which of these Eli and ice does that occur? That's in Eli, and that's associated with this inductive load. That means you have a positive Q, and we will say that that's a lagging power factor. That's some more terminology or information that you can use to extract or to sketch this power triangle. Conversely, if somebody or if your system happens to have a negative angle theta, then that corresponds to your current leading your voltage. That's now the ice. I is coming before V in that expression. That now gives us a capacitive load. Bless you. Q is now negative, so now we would go down, and we would refer to that as having a leading power factor. Questions on that? Question?
What is negative Q, negative imaginary power?
So now negative imaginary power just means that you have a load that has more capacitive looking component than inductive component. It looks more like a capacitor than it does an inductor. And in the power triangle, all that means is that if you really did have a leading power factor, then instead of going up with Q, you would go down. It would be in the negative direction, and your angle would be below the real axis.
What physically does?
So physically what that means is if you had a capacitor, and only a capacitor, then you would have negative reactive power. Your Q would be negative. The imaginary part of that power would give us a negative value. Question?
So if you were one of these big industrial customers of the power company, and you had a bunch of negative reactive power, they would charge you for the reactive power.
The question was, if you're a big industrial user of power and you happen to have a lot of capacitive loads, the power company would probably love you because everybody else has lagging or inductive loads. Most of these big industrial facilities have big motors or machines, and there's a lot of wire, coils of wire, and those are like inductors. So usually what you have to do as an industrial user is if you're sitting off here from a substation and you're absorbing all or getting all this power, you look like a big inductor to the power company, which gives you a positive Q. You may get a surcharge or a tax on that basically because you are using a lot of apparent power for the real power that you really are consuming that's driving your loads, crushing your corn or whatever you're doing. Because of that, the power company is going to charge you more. Well, you might say, you know what? I've had 207. I know how to get that angle down. So you put in some capacitor banks to supplement or augment your motors. and you now try to lower that angle to maybe make your power factor 0.9 instead of having it at 0.7. And that's what we'll do after I give you this class participation problem. But did that answer your question?
So the answer would be no. They wouldn't charge you for capacitive load because
The question is, are they going to charge you for a capacitive load? In today's economy, if you have a leading power factor, they may charge you if it's 0.7 because that's going to take a lot of apparent power. They may say, I don't care, you're off in your own little world, you have a lot of apparent power that our power lines are having to be designed to withstand, and so we're going to surcharge you for that also. It's just that most industrial users, their power factor is positive, or their reactive power is positive. They have a lagging power factor. But if you had a big capacitive load, they would probably give you a surcharge also. So this is basically find the powers in terms of this question. I want you to find the real power, the apparent power, the reactive power, and the power factor given the following system. Whoops. And I'm in a good mood. That's already in RMS. There you go, you're welcome. Here's your load. With that, find the real power, the reactive power, the apparent power. That's a pretty poor F, but Fs are usually associated with poor. Sorry. So there's power factor, and find that also for that particular system. I'm telling you that maybe that's the load sitting out there, and they can measure now this voltage drop across that load, and they've measured it to be 50 RMS at an angle of 10 degrees. How about I give you 2 more minutes? Make sure your code number is on your paper and pass those to the appropriate location that we've learned over the course of the semester. And after that, class participation, if you're looking for a few more points in your class participation column, there's the advertisement again for tomorrow afternoon. This class participation might be worth 5 points, possibly, meaning handing in a paper with a code number might get you 1 point. Getting an average power might give you a 2nd point. Getting the reactive power might give you a 3rd point, and apparent power a 4th point, and a power factor a 5th point. Pass them in, and over the course of the semester, hopefully you will accumulate quite a few of these points, and I'm hoping, that if you acquire, let's say, half of the points on average, then you'll basically be given all of the class participation points. Is that making any sense at all? Probably not. But if you, over the course of the semester, if we have 100 points possible, where this one was 5, maybe we'll have 150 points. Maybe I'll say, you know what, if you've accumulated 120 class participation points out of 150, you'll get all 10% of the class participation points. Does that make sense? I haven't even decided because it's going to depend on how many class participation points we have over the course of the semester. Let's look at this particular problem. What's the impedance of our load? If I said, just give me the impedance of the load, wow, everybody leaves after they've done their class participation. Or maybe I should do it this way. Let me just say that this is, I don't know where that came from, R plus Z sub L, where my Z sub L is already in J4 form. This is now 10 plus J4. The reason I might be interested in collecting, those are in series, they just combine. There's my 10 plus J4, that's my load. And I have the voltage dropped across that load, which means I can pretty easily find my current. That's just this generalization of Ohm's law. V is equal to ZI. Or if I solve that for current, my current phasor is now my voltage phasor divided by Z load, or Z sub L. And this is now 50 at 10 degrees. That was given. And we divide that by this complex number, 10 plus J4. If we're doing division, it's probably best to convert that to polar form, a magnitude and an angle, so that we just have to take the difference, take the quotient of the magnitudes and subtract the angles. If we convert that to a magnitude and an angle, did you end up with 21.8 degrees for your angle and a magnitude of 10.77? No? Oh. Like I said, it's not that critical. I just want you to start to be, the more critical part of these class participation is to get you engaged and thinking about what I do or do not know. And then maybe these little pieces of lecture will become more meaningful, is the idea. I sub L now, we simply take the ratio of that, so we're expecting to see a current of about 5 amps in magnitude. It's 4.642. The angle is going to be 10 minus 21, or minus 11.8 degrees. Meaning, relative to the voltage, this current's angle is below it, or it's lagging the voltage. This seems to be an inductive load, which is what I sketched, right? I sketched an inductor. So it looks like we should be fairly consistent that way. What's our complex power? If I now have the voltage of the load and the current for the load, I've got everything that I need to find all the answers. My complex power how did we define that? If you know the voltage and you know the current of whatever it is that you're trying to find the complex power for, you take the voltage phasor and the current phasor. The complex conjugate of the current phasor. I was waiting to hear some, wait. It's VI star. That's your complex power by definition. We now know those two pieces. V was given. That was 50 at 10 degrees. I we just calculated. That had a magnitude of 4.642. And we know that's in RMS units because we started with voltage in RMS. And the impedance is just going to scale it. We don't have to worry about converting the impedance to an RMS quantity. We know now that we started with an RMS 50 volts. The current that we find using that voltage will give us our RMS current. What's my angle in this product? It's either the conjugate of minus 11.8 or it's just the negative of that, which is 11.8 degrees. I multiply those two together and I now have 232.1 at an angle of 21.8 degrees. And that's the same angle as my impedance, which is fine. Now we can sketch this if we want to get a feel for what we have. What we so far have determined is an angle of 21.8 degrees and a length of 232.1. That's actually our apparent power. Question?
So the complex power, I
So the complex conjugate of our, whatever it is that we're finding the complex conjugate of, that's just negating the angle. If I have a complex number, 5 at 30 degrees, and somebody says, oh, find the conjugate of that, that's 5 at minus 30 degrees. Here we started with a current of 4.6 at an angle of minus 11.8. So now we just need to negate that minus 11.8 to give us our plus 11.8 to find the conjugate of that current. This is what we now have. But now that we have that picture, meaning you may want to bring your compass and your rulers so that you can sketch all of these. You can now draw these angles. You could sketch these accurately, and then instead of having a calculator, you could just draw these and measure the distances. You now know the average power, which is right here. That's this real part, or the adjacent side of that right triangle. And here is our reactive power, Q, to get us up to that tip of the complex power phasor right there. Or we can now find those components if we wanted to analytically. We had 232.1 at an angle of 21.8 degrees. That's what we computed to be our complex power of the load. We can now take the cosine of 21.8, scale it by 232 to obtain a value of 215.5. And we have our reactive power, which is the sine of 21.8 times 232, and that gives us 86. And we now have our P average plus our JQ. And these are, maybe I should be more, let's call this Q sub L, and let's call this P sub L. So that now my P average is P sub L, which is 215.5. What are the units? Watts. My reactive component is Q sub L, and the sign of that tells us whether it's leading or lagging or inductive or capacitive. That's a positive 86. That has units of volt amperes reactive, or VARs. That went up in our picture of our triangle. Our apparent power. The power that the power company is having to produce is the magnitude of the complex, or that's the length of the hypotenuse. And that was 232.1, and that has units of volt amperes. Now we have 4 of the 5 points. Hopefully you remembered your code number. That gave you one of those points. See, just showing up gets you something. And who knows what you'll find tomorrow when you show up. What? Huh? Commercial. You have an attention span of not very much, I'm told, in a class because your lectures are usually quite boring. So I have to somehow wake you up. Every 11 minutes, I think, is what you last. Usually you're too worried about who sent me that text? What? What? I really need to do that tonight? Huh? Sorry. I'm texting and I'm doing all these other things up here. You don't know that, do you? So 0.928 is the power factor. Have I given you everything I need to give you on the power factor? Is it leading or lagging? Is Q up or down? It's up, which means it's an inductive reactance. And in an inductor, you've got Eli, and the current is lagging or behind the voltage. So this is a lagging power factor.
Theta would have to be negative, for instance.
Theta would need to be going down or negative to be leading, to have a leading power factor. But if you take the cosine of that negative angle, that wipes out that information. So if somebody just gives you the number 0.928 and says, oh, your power factor is 0.928, you don't know whether it's leading or lagging without that additional piece of information. If they give you the angle, you know it's positive or negative. Oh, it's lagging or leading. But if they just tell you the power factor and don't tell you leading or lagging, you're missing some information. Is that clear? That's why that additional information is important if you just state the power factor. Questions on that? How many got all 5 points? Oh, I was feeling so good today until that result. Oh,
That's another problem now.
I could give you another problem. Oh no,
Yeah, redo.
now redo. Give us a redo, a retake. Oh, now everybody starts passing their corrections to the right or to the left. Let's do another example. You'll get more chances, but that just means maybe I wasn't very clear in the earlier part of the lecture, or maybe I hadn't. No, you can't start passing your paper now. No. So here's the transmission line. Suppose somebody gives you a transmission line that has an impedance of 1 ohm or 1/10 of an ohm per mile. And let's say that the plant, that's where you're operating, the plant is 1 mile down the line. And they tell you at the plant that the voltage at the plant is 480 volts at 0 degrees. And they say, oh, that's your RMS voltage. And they also tell you that the plant is consuming 120 kW, kilowatts, at 0.85 power factor lagging. And you thought you were finished with these word problems. Now I can give you a bunch of word problems for exam 2, right? Goldilocks walks down the alley. Underneath the voltage transmission line. Sorry. Okay, like I said, what's the question? Is there a question there in all that verbiage? No, I haven't asked the question yet, but can you anticipate the question? The verbiage was so long it scrolled off the screen. Can you remember some of it? We have a resistance of 1/10 of an ohm per mile, and we're 1 mile down. The question is, what is the voltage and the power? Oh, power factor. At the supply side of the line. What in the world? Okay, the plant is at the load side. Oh, I'm not supposed to sit on the furniture, am I? Sorry. The plant's at the load side, and now we want to walk a mile towards the supply and measure the voltage over here a mile away, and we want to know what's the power factor this far away from the plant. At the plant, what do we know? We know the power factor is 0.85 and it's lagging. We have an inductive load, and what else are we told about the plant? What kind of power were we told in the problem statement? We were told the real power, weren't we, or the average power, because we were given kilowatts. If we were given something else with different units, we would have maybe been told the magnitude of the apparent power. If we would have said, oh, your plant is consuming 150 kVA, then that would tell us the length of our complex power vector. I need a picture. To get my hands around this particular problem. Here's my load. Doesn't that look like a load? And what do I know about the load? It's 120 kW. It's 0.85 lagging. That's the load. And I also know that I'm traveling a mile away, and a mile away, or over the course of that mile, the length of that transmission line between the supply side, which is over here, and the plant, or the load, I have a resistance of 0.1 ohm per mile. So effectively I can collapse or consolidate all of that resistance into a discrete resistor that I'm going to say is 0.1 ohms.
Since it's AC power, it's going back and forth. Is it really 2 miles from there to that?
Okay, so now, man, you're making my head hurt on that question. The question was, we have AC power, don't we? We are pushing power, well, the voltage and current are going up and down, plus and minus, which means that you could think of this as sort of going and coming, going and coming. We will just worry about the net effect, basically, and the length of that wire is 1 mile. The question was, do we have to worry about it going and coming being any incorporated into the distance? No. Let's just view that as one length, which is a mile, and that 1 mile of cable has an impedance or a resistance of 0.1 ohm. And we're going to lump that into our circuit here of our supply side and our load side as just a discrete resistor of 0.1 ohm. The other piece of information that we were given was we were told what the voltage dropped at the load was. And we were told that that was a magnitude of 480 at 0 degrees, and that we were, I think, told was RMS. With that picture, so that's the word problem transferred into a circuit or into a picture, that maybe should make you feel a little bit more comfortable or a little less anxious. What we want to do is find that phasor, V sub S bar, and we want to find the power factor at that location. Power factor of our source. What is going on? Well, really, if you were just looking at this to get a feel for it, what does this sort of look like to you maybe if you try to relate this to what you learned earlier in the class? Does this look like a mesh problem? Are you starting to see maybe that this is, oh, here's my source, here's a resistor, and here's basically a complex resistor, let's say Z sub L, here's R sub line or transmission line. So here is a load. We could say this is load 2. Here is load 1. And now this is my supply right here, V sub S. If that's what I have, then I could actually find this voltage drop by writing a KVL around that mesh or around that loop. Question?
Can we assume, since it's lagging, that it's only an inductive load and not a combination?
The question was, since it's lagging, can we assume that it's only inductive, or do we have to worry about it being a combination? It's a combination of real and imaginary because it's not a purely inductive load.
But do we have to worry about
We don't have to worry about the capacitive component. We're now told the relationship between the imaginary part and the real part by the power factor number. Now that we know the power factor is 0.85, you could now find the angle associated with the complex power of that load in this green box. So we now, if I'm calling that load 1, this is now effectively load 2. That does not have any reactive component. That's all resistive, or that's all real.
But in the green box, is there a capacitor?
But in the green box, is there a capacitor? No, essentially what we've done, even if there are, there's more inductors there, so that the net effect is that we're going to just look at that as like lumping that into an inductor. The inductance and the capacitance all combine such that it effectively looks like an inductor and a resistor in the combination to give us a cosine or an angle such that the cosine of that angle is 0.85. Is that making any sense? Which, what I was trying to do in that second figure was to convince you that if we could figure out what this current is, then we could figure out what this voltage drop is. And once we have that voltage drop, all we really need to do is walk around here, and in so doing, we now have determined what this supply voltage is, because we will know what this drop is, and we were already given what that drop was. That was 480. Meaning, if we can find this current, we're almost done, because that current times the resistor will give us the voltage dropped across that second load. Once we have that, we can sum that with the 480, and now we have our source voltage. Is that making any sense? Once we have the source voltage and we have the current, we can figure out what the angle is of the source. And once we have that angle relationship, theta sub s, or say theta sub v sub s minus theta sub I, then we have our power factor of our source. That's where I'm headed, or trying to get to. Meaning, I know what the voltage dropped across the load is, and I know the real power. Now is when I need to start remembering all of those observations or those relationships that I had before. P load I was given. That was 120 kilowatts. But that's V RMS, I RMS, cosine of theta load. What do I know in that formula? What was given? I've already written some of it. That was a given. What else was given? Theta was given, so effectively this was given. Because I can take the cosine of, well, actually the cosine of that angle was given, wasn't it? I was told the power factor was 0.85, so I really was given cosine of theta sub L. That's 0.85. Question?
I got lost. What is the T subscript?
I don't know. What did I call the T subscript? T is for transmission line. So R sub T is my transmission line resistance. Thank you. I'm just throwing coefficients everywhere. Sorry. But that means the resistance of my transmission line, which was 0.1. And Z sub L, maybe I don't need to find that, but this is the concept that I'm trying to do. I just need to find something that will give me this current I. That's what that second picture was trying to convince me of. Was there a second hand, or did I answer it? What else were we given? Were we given anything more at the load? We were given this, weren't we? We now have 3 of the 4 variables known. This was 480. This was 0.8 whatever, 5. We can now solve for the magnitude of our current. Meaning I now know IRMS is going to be P load divided by VRMS times the power factor of the load, which is what this is. I now have 120 kilowatts over 480 over 0.85 to give me a current. Hopefully Goldilocks is not close to that transmission line, because that's 294 amps. That's enough to fry anything. Okay? That's a lot of amps. How many amps are flowing through your hair dryer? Less than 1? How much? Well, it depends, I guess, on your voltage, but out of most of your circuits in your home, what's coming out of the wall, volt-wise? 120. What's your hair dryer? 1 kilowatt, right? 1,000 watts. That's a home. So now you have 1,000 divided by 120. This makes my 102 class really nervous. Let's just say, oh, that's 1,000 divided by 100. You can't do that. Well, I'm trying to get a feel for what's going on. Okay? So they want 6 significant digits, but we're engineers. We want to just get a feel. So I now have 1,000 divided by 100. That's 10 amps, right? That's what you're drying your hair with. That's why you don't want to be in the bathtub drying your hair, okay? You're playing with fire. You don't want to be wet or get grounded or have any of that current bleed through. You did the problem, right? Your homework problem. You've got 10 amps. How many amps do we have here? Whew! Almost 300. 30 times that. Supplying this load. This load was 120 kilowatts. That's this class drying their hair at the end of that wire, right? At the end of that transmission line, you're all with a hair dryer drying it, because we have about 120 of you today. 20 of you just left after the quiz. That wasn't funny, but okay, I'll take it as funny. Where were we? Drying our hair. 294 amps. Sorry, had to wake you up. Where were we going? Oh, this now tells us, what does this tell us? What can we use with that? Can we find anything relative to the second load, which was our transmission line, which was R sub T? I now know the current. I squared R, right, will give me my power on that transmission line. So the power on the line is now I sub RMS squared times the resistance of the T, or maybe I should say that confused everybody, so let me call that the resistance of the transmission line. That's now 294.1 squared. That's why it doesn't take a whole lot of resistance on that transmission line to amount to something. How much power have we lost just on the transmission line? 8,650.5 watts. 8 hair dryers, almost 9. Just to supply you guys to dry your hair. Okay, we're in the desert, just air dry it, okay? Save some energy. Be green. Go to class with wet hair. Well, maybe not in the winter, but early or during the summer, that's fine, right? Or if you're like me, it doesn't look like you did anything with your hair, probably. But we have 8,000 watts.
Why is it IRMS squared?
IRMS squared. Because we need to have RMS units, we could think of this as many different things, couldn't we? We could say that this was VRMS, IRMS, and because it is purely resistive, what do we know the angle of our resistor is? What's the relationship between our voltage and current on a resistor? They're in phase, aren't they? So theta sub R is theta sub V minus theta sub I for that resistor. Those angles are the same, whatever they are. So theta sub R is 0. This is now 1. And what is this on a resistor? Ohm's law. So this is I times R. Where this current is there, there's my I squared R.
We just use I squared R because we don't know the V on the resistor.
Right, we don't know the V on the resistor, so we just use the formula that will give us the power in the units that are in the variables that we already know. Does that help? All right, finish up this tonight. Tell me tomorrow at the lecture what you come up with on drying your hair. I'll see you on Tuesday.